Good morning to all of you.
Good morning,
Morning.
sir.
Yeah, good morning. Good morning to all of you. Is my screen visible?
Yes, sir.
Yes.
Are there any questions, doubts? Is anyone having any question or doubt? Okay, so if there are no questions, I am starting. So today, the last class we discussed how we can use the assembly of plate elements to model more complex structures. Today I am going to discuss. We have talked because in the the reduced integration elements or selective reduced integration elements are popular in packages. So, but to actually one has to overcome this hourglass modes. So to control the hourglass modes, there is a stabilization matrix, additional stiffness matrix, and sometimes additional damping matrix is added. So I'm going to talk about that aspect today because that's an important thing. Because in the softwares you have you most of the time you end up using reduced integration elements with hourglass control. So that I want to discuss today. So that is I'm going to the topic is hourglass control for
Hello, sir.
four nodal. Yeah,
Sir, in selective integration also, do we have R-class modes?
yeah. In the you have both in the reduced integration and also in the selective integration. Of course, the number would be less in selective integration.
Okay, sir.
So hourglass control for four noded isoparametric element. With reduced integration. So I'm going to talk about reduced integration. So now what we are talking about is a isoparametric element. So that means we have element arbitrary quadrilateral in physical coordinate space. This is mapped to a square in the natural coordinate space. And if you look at the stiffness matrix for this element, I'm going to talk mainly about the stiffness matrix. So it consists of two parts. Oh, it is not writing, so let me close and open it again. So is the screen visible now? I closed it in between. Hello, is the screen visible?
Yes, sir.
Okay. So I said this, the stiffness matrix for this element is consisting of two parts of the bending part and the shear part. We have two parts in the stiffness matrix of the element. Of course, I am only talking about the element where W, theta x, and theta y are the degrees of freedom. So we know that this bending part of the stiffness matrix is when we do the numerical integration, so I going from 1 to m, j going from 1 to m, and then we have b transpose into d into b into determinant of the Jacobian matrix evaluated at xi I eta j into wi wj, and the shear part of the stiffness matrix is also evaluated using numerical integration, I going from 1 to ms, j going from 1 to ms, and then we have bs transpose into e into bs into determinant of the Jacobian matrix evaluated at xi I eta j wi wj. And for the reduced integration, we know that in case of reduced integration, we use both m and ms is equal to 1, so it's basically 1 point integration. Of course, in the selective integration m is 2 and ms is 1, but in the reduced integration m and ms both are 1. So now to talk about this hourglass control, let me define some basic quantities which we would need in this. So define the following. So let us say define a vector s. So s is and it's basically 4 rows in this. So 1 1 1, this is s, and this would actually typically represent the rigid body motion. So if all the 4 nodes have got same w, then that's a rigid body mode. So this vector s is actually representing the rigid body motion. And then let us define vector h. So let us say this vector is 1 minus 1 1 and minus 1. So this depicts typically the hourglass mode. So like alternately at the nodes you have w positive, then negative, positive, negative. So this would represent the hourglass mode. This h would represent hourglass mode, where the w is alternately plus and minus, or theta x is alternately plus and minus, theta y is alternately plus or minus. And in addition to this, because now for the calculation of the b and bs matrix, we now need the derivatives of the shape function. So we define this vector b1 is integration over area of the element del by del x of vector n. So this is a vector of shape functions is equal to a. No, this is the vector we are defining b1, and here again where this vector n is shape functions n1 n2 n3 and n4. And similarly we define vector b2, which is the derivative of the shape functions with respect to y. So del by del y of nda. And if you look at these vectors, and if you look at these vectors, they satisfy some properties. So but before that, now if you look at this vector b1, so actually if you do the calculation, vector b1 can be written as let me write in the column format. So b1 transpose can be written as half of this vector consisting of y2 minus y4, y3 minus y1, y4 minus y2, and y1 minus y3. So this finally, if you do this integration, the differentiation and then the integration with respect to area, this is what you get. And similarly, if you look at this vector b2 will come out as half of,
Hello, sir.
yeah.
Sir, can you please explain again that S vector, like what are those 4 rows represent? Are these the
So
degree of
four
freedom?
rows are corresponding to actually 4 degrees of freedom, either corresponding to w or theta x or theta y. 4 rows are, let's say we have 4 nodes in the element, and if we look at w, so w1 w2 w3 w4, so these are those 4 rows. So I was saying that it represents rigid body mode. So let us say w is same at all the 4 nodes. So let's say unity. So W1, W2, W3, W4 all are unity. So it is representing that. And similarly, the vector H is representing an hourglass mode. So again, if you look at the W values at all the four nodes of the element, so they would be alternately plus and minus, plus 1, minus 1, plus 1, minus 1. So that is representing an hourglass mode. So this is representing four values of W, say at the nodes of the element, corner nodes of the element, W1, W2, W3, W4, or no, theta x at four corner nodes, theta x1, theta x2, theta x3, theta x4.
Okay, sir.
Okay.
Thank
Yeah. And so then this similarly, no, if you actually do this calculation, you can show that B2 transpose would be half of x4 minus x2, x1 minus x3, x2 minus x4, and x3 minus x1.
So can
So
you get the physical meaning of B1 and B2?
what is yeah, b1 b2s are nothing but if you see here, it is defined here, no. B1 is the integration of del n by del x over the area of the element, and B2 is integration of del n by del y over area of the element. That is what I have defined here, where n is the vector of shape functions n1, n2, n3, n4. So they are representing basically the no, the average value of you can say the gradients of the shape functions. B1 is representing average value of the gradient of the shape function over the area of the element with respect to x, and B2 is representing average value of gradient of shape function with respect to y over the area of the element. So be divided by area, it will directly give you average values of gradients of shape functions with respect to x and y.
Sir, here shape functions are in the in the physical
Yeah,
coordinate
yeah.
system.
Say functions are in the natural coordinate system. Yeah, Commander Harsh, I have a class actually. I'm taking class right now.
Right, right.
Sir, and
So
after integrating, sir, after taking the derivative and integrating over the area, and then
yeah,
again you are converting it to the physical
yeah. So
coordinate
this
system.
this
Is that
can be
right?
written. Yeah, this can be finally the answer would be in terms of these coordinates, because see, dA you will write determinant of j into d I d eta, and the derivatives you would write no in terms of inverse of the Jacobian matrix, and derivatives with respect to xi and eta. So finally you will find it no, if you do this calculation, you will find that this will come out in this form and in this form directly. There is no conversion in between. It's a straightforward no, if you carry out this differentiation and then integration, dA in place of dA will write determinant of j into d xi d eta, and you carry out the integration, you will directly get b1 and b2 in this form, the way I have written.
Okay, sir.
Yeah. So now if you look at these vectors, they satisfy some orthogonality properties. So let me write those. You can actually check yourself that, so these vectors satisfy the following orthogonality relations. So you can actually check that. You will find that you will, if you take the S transpose into H, so this will be equal to 0. If you take S transpose into B1, this will be equal to 0. If you take S transpose with B2, that will be equal to 0. These are straightforward, no, you can cross check. And similarly, if you look at the H transpose into B1, that would be equal to 0, and H transpose into B2 will be equal to 0. You will also see that if we take no vector x, I'm going to define x. What is x? So x transpose into B1 will give you the area of the element, and x transpose into B2 will turn out to be 0. Similarly, y transpose into B1 will be 0, and y transpose into B2 will be equal to area of the element. So here I have not defined xy, so let me define those. So where vector x is the x coordinates of all the four nodes, so x1, x2, x3 and x4, these are the x coordinates of all the four nodes, and vector y is y1, y2, y3 and y4, and I just said a is area of the element. Now if we talk of zero energy modes, let me talk of no, not all but few zero energy modes. So because we are ultimately trying to control the hourglass modes, so zero energy modes. So one is, now if you take the element, let us say this is the element, and then if we take the rigid body mode, which is translation, the translation along x, so we will have at all the four nodes we will have same w. So if you look at the deformed shape of the element, that is going to be like this will be the deformed shape of the, so this is rigid body mode. I'm only showing few of these rigid body mode. And now if you look at the bending modes, the constant curvature modes, so the constant curvature modes would be, let us say in one case we have rotation about y axis. So originally the element is like this, and then because of the rotation, one side the w would be positive, other side w would be negative, so it would be like this. So you will have the deformed shape of the element is going to be like this. So, and similarly there can be other bending mode, that's the due to rotation about x axis. So in that, let us say one side the w is positive, other side w is negative. So when you plot the deformed shape, the deformed shape is going to be like this. So that would be the deformed shape. These are bending modes. And then if you look at one of the hourglass modes, I will just demonstrate, so only one hourglass mode. So if you have let us say the original element is, this is the original element in the undeformed configuration, and we know in the hourglass mode there is a this node, let's say the w is negative, so then this node w would be positive, again this node it would be negative, this node it would be positive. So you see alternately it is positive, negative, positive. So if you look at this deformed element, it would be something like this. So if you see, this is hourglass mode, that is alternately w is positive, negative at the node. Similarly, you can have hourglass modes corresponding to theta x and theta y. So theta x would be alternately positive and negative at the nodes. So similarly theta y and so on. So these are the all these are zero energy modes. And if I list down all of them, so if I look at all the, this is, I have depicted only few. One rigid body mode, two bending modes which are constant curvature modes, and the one hourglass mode. Let me write all of these. So let me write for each of these. So if I talk of 1, 2, 3, there's rigid body modes. So you will have three correct rigid body modes. So now let me under the rigid body modes, let me talk of under the zero energy modes. Let me first talk about rigid body modes. So there are three, as we know, correct rigid body modes, and in this, if you look at W, theta x, and theta y. So if you look at the W as a vector, so that is W1, W2, W3, W4 at 4 nodes. Similarly, theta x as a vector, theta y as a vector. So you will find one rigid body mode is a translation. So in that, W would be equal to vector S. Of course, the magnitude need not be unity. It would be some value. So you can always normalize the that vector. So it would be S, and in this, theta x would be a null vector, theta y would be a null vector, and this is translation along Z. So this is a translational rigid body mode. And then you have mode number 2 is the x rotation. So x rotation, as we know, is the rotation about x axis, will be let's say s plus s or minus s. So rotation about x axis will come in theta y. So this is s, and see, this is 0, and then you will have this w. So there is a rotation theta y is there, rotation about negative theta y is the rotation about negative x axis. So that will lead to the displacement which are proportional to y. So you will have this w as minus y. And then if you look at the rotation about y axis, which is theta x, that is s. So all the four nodes have same value of rotation. The rotation about y axis would be 0, and then this will be x. The w in this mode would be x, proportional to x. So this is x rotation about x axis, and this is y rotation. So these are the rigid body modes, and these should be there. I know when you have an element, obviously when the element is free, these modes should be there. Now when you talk of hourglass modes, so hourglass modes again, say 1, 2, 3,
Sir, how the
and
x and minus y came?
now if you say, if here s is the rotation about negative x axis. So now if you look at, if there is a rotation about negative x axis, so let me sketch over here. So if there is a rotation about negative x axis like this, so because of this rotation, these nodes will the displacement would be in the z direction. The displacement would be proportional to y, and because of rotation about negative x axis, these will move in the downward direction. And if this is y coordinate is 0 here, then this displacement would be 0. But let's say no, that value is some non-zero value, or it's actually 0. So because of this rotation, which is no, this s, because of this rotation, the w displacement would be in the downward direction and would be equal to rotation into y. So that is why rotation is unity, s is unity. So y, the displacement would be simply y. And similarly for the third mode, when there is a rotation about positive y axis, so that rotation is unity, so the displacements would be proportional to x coordinate.
Okay, sir. Thank
Yeah.
Theta x, theta we can present together, right? Can there will be
Uh,
rigid body modes?
yeah, theta x, theta y. If both, yeah, there no, yeah, there may not be decoupling if you get the eigenvectors as it is. So there might be coupled mode, but still you will have three correct rigid body modes. So that means if you plot the deformed shape of the element, it would still be a flat surface with some displacements of its nodes. Then now if you look at the hourglass mode, so one is hourglass in W, so that would be H. So alternately W is plus minus at the node, so that is hourglass mode. And in this W hourglass mode, theta x and theta y would actually be 0. So this is W hourglass. Then you will have in this case, let's say theta x hourglass. So theta x means the rotation. Let me theta x hourglass means in terms of theta x. So that would be here. You will have h, and this at 0. So this is theta x hourglass. In the theta y hourglass, you will have these two as null vectors, and this will be equal to h. So that would be theta y hourglass. And then there is a, for the reduced integration, no, that's one more mode, which is a twist mode, the fourth one. So in this you will have rotation, no, the theta x and theta y would be, let us say, proportional to x and y coordinates, and then w would be equal to some constant a1 into x plus a2 into y, and this is a twist hourglass mode. For the constants, let me define here. So where a1 is 1 by 4 s transpose into y, and a2 is 1 by 4 s transpose into x. So because here you see the rotations themselves are proportional to nodal coordinates of the nodes, and then further the w displacement would be proportional to x and rotation. So those constants are depending on the coordinates again. And then the this is twist mode. Of course, more important are these three hourglass modes. So when we look at the the solution, we have to mainly what is more important is that we control the first three hourglass modes, that is w, theta x and theta y hourglass modes, because if these modes are present, you will get zigzag deformation pattern of the structure when you analyze, and if these hourglass modes are present, so then that is what you will get. So now what do we do? So this is some preliminary about these hourglass modes and the with some basic vectors we have defined.
Sir,
Yeah,
for if one node have 5 degrees of freedom like u, v, w, theta x and theta y, then
yeah,
rigid body mode will be 5 and
yeah. Then it
hourglass
will
mode will
have
be
five.
6.
Yeah, it will have five rigid body modes. Here, what we are talking about is only 3 degrees of freedom: w, theta x, and theta y. So that is why
And
three rigid
6
body.
hourglass mode.
Yeah, hourglass modes also would be more depending on what is the integration scheme you are using.
Okay.
So now we because what happens is, if you use this element, this reduced integration element for thick problems, so these hourglass modes would be activated, and if they are activated, you will, if you look at the your mesh, deformed shape of the mesh, you will see that it would be kind of zigzag. Alternately, the nodes will have positive and negative displacements and rotations. So we need to control that, means we'll have to add an additional stabilization matrix so that these modes are not activated. So in order to control the hourglass modes, we define these are corresponding to hourglass modes: generalized displacements qi, and which are activated by these modes, that is hourglass modes. but vanish in rigid body motion. So these generalized displacements are activated during the rigid body modes, but if we look at these generalized displacements corresponding to rigid body modes, so they should be zero. So but no, these generalized displacements we are talking about, they vanish in rigid body motion.
Hello, sir.
Yeah,
Sir, in the hourglass modes, you have
yeah,
told that there will be no energy that will be associated.
yeah, right.
So, but by looking onto the shape of this mode, it is, I mean, will there
No, you
not be any
cannot just say, you
localized?
have to calculate. If you calculate the energy, you will find that it would be zero. Strain energy, if you calculate corresponding to these deformations, you will find that it is going to be zero.
Will there be localized strain in this mode?
No,
Okay.
the strain energy, if you calculate, it is going to be zero for the element. No, there is no strain energy corresponding to these modes, all the hourglass modes. Their net strain energy is going to be actually zero. So let us say define q1, qi I said. So q1 is a generalized displacement, and this is defined as some vector gamma. This gamma is different. This gamma is not the transverse here. We are going to define this gamma, but I am using that same notation. So let me call it as gamma bar, which is a different quantity, into w, and w, that means this would be corresponding to w hourglass mode. So this will be to control w hourglass mode. W hourglass mode where vector w is equal to h. And now we want to this whatever generalized displacement we are defining, so we want it to be zero for the rigid body mode and non-zero for the hourglass mode. So we want q1 to satisfy the following, as I already stated in the this statement what I have written here. Those conditions are that when we calculate q1 for the rigid body mode, so that is q1 is equal to gamma bar transpose into wr. Wr means rigid body mode, so this is 0. Let me call this as equation 1. And when we calculate this w for the hourglass mode, so gamma bar transpose into wh. When we do wh means hourglass, so this will not be equal to 0. So let us say this is equation 2. Now what are wh here? So I have already stated where wr is arbitrary small rigid body motion. Arbitrary small rigid body motion or displacement, you can say. And wh is the hourglass mode, hourglass displacement or deformation, hourglass motion. Now the as far as wr is concerned, for wr would be a combination of, so now if you look at the wr for arbitrary, what we have talked about here, these three rigid body modes, where we talked about translation, x rotation and y rotation, but for a general rigid body motion it would be combination of all the three. So we can write that as some constant beta 1 times s plus beta 2 times x because of rotation, one rotation, and beta 3 into y because of the rotation. This would be because of rotation about x axis, and this would be y axis, and this would be because of rotation about x axis. So that would be arbitrary rigid body motion. So that is what is wr. Now what should be the form of this gamma bar vector? The vector gamma bar, that vector gamma bar is also known as hourglass shape vector. So we let us take that is taken as a combination of this vector h, which is alternately plus and minus 1 at the nodes, and the combination of derivatives of the shape functions integrated over the area of the element with respect to x and y. So this hourglass shape vector gamma bar is taken as a combination of h. Obviously we have to have h because that is what we want to control, and plus we have some constant alpha 1 times uh, b1 and b2 we have already defined, and alpha 2 times b2. Now once we have defined this gamma bar, so you will see that equation 2 is going to be automatically satisfied, because when I take gamma bar transpose into wh, and wh is can be simply, let's say, h itself. So b1 into h and b2 into h would be 0, but h transpose h is going to be non-zero. So this is actually automatically satisfied, and we have to find out alpha 1 and alpha 2 such a way that this condition is satisfied, that is condition in equation 1 is satisfied. So let me write what I just said. Equation 2 is satisfied, as I already said, and equation 1 requires that basically. Now if you look at the your gamma bar vector, so the gamma bar vector is gamma bar transpose would be h transpose plus alpha 1 times b1 transpose plus alpha 2 times b2 transpose. This is the gamma bar transpose into a rigid body, arbitrary rigid body, which is beta 1 into s plus beta 2 into x plus beta 2 into y, and this should be actually equal to 0, and this should be true for all beta 1, beta 2, beta 3. So this would be true for all beta I, that is beta 1, beta 2 and beta 3. So now if it has to be 0, this product has to be 0 for, that means whatever shape no hourglass shape vector we are getting, this should be orthogonal to the rigid body mode. So that means it should, that meaning is that it would be activated only when the hourglass modes are active, and this would be null vector when only rigid body motion is taking place. If the element is moving rigidly or the mesh of element is moving rigidly, then this vector has to be actually 0. So it is orthogonal to rigid body modes. So that is what it is denoting. So we have already talked about these are if you multiply all these both together, and then the coefficient of beta 1 should be equal to 0, coefficient of beta 2 should be equal to 0, coefficient of beta 3 should be equal to 0, and that is for because it should be true for any arbitrary rigid body motion. So if you use the orthogonality relations which I have listed over here, so if you look at these orthogonality relations which are listed over here, if you look at these orthogonality relations, so you will be able to show that this will lead to. So let me write using orthogonality relations, we will be able to get alpha 1 is equal to minus h transpose into, you can, it's a straightforward calculation. Now this multiplication will have 9 terms from the orthogonality relation. Some of these would be 0, some of these you can write in terms of area, and then you will be able to get, and for the coefficient of beta 1 equal to 0, coefficient of beta 2 equal to 0, coefficient of beta 3 equal to 0, because this should be true for all beta. You will get alpha 1 as minus h transpose into x divided by area of the element, and alpha 2 you will get minus h transpose into y divided by area of the element. So now finally you can therefore say that this hourglass shape vector gamma bar will be equal to h, and then minus 1 upon a, and then we have this h transpose into x into this is b1, and minus 1 upon a, then you have this h transpose into y, this will be a scalar, into b2. So this whole thing, yeah, this is what is going to be b1 and b2 are vectors. So this is what is going to be your gamma bar vector, and we are going to construct the stabilizing, the stabilizing yeah, matrix, stiffness matrix, using this gamma bar vector, shape vector. So this is to control, this form of gamma bar is to control the W hourglass. So similarly, the second and third hourglass modes, which are theta x and theta y hourglass modes, can be controlled by, so the second and third hourglass modes can be controlled by taking another set of cues. So let me take that as q2 as so q2 and q3 we are going to take as a gamma transpose into, say, let us say q2 is equal to gamma bar transpose into theta x, and q3, the third generalized displacement corresponding to the hourglass mode corresponding to theta y, would be gamma bar transpose into theta y. So no, like that, no, you can take these modes now. So once we define this generalized displacements q1, q2 and q3, then we talk of corresponding generalized actually forces. So for each, because no, ultimately we'll have to, corresponding to the hourglass deformation, we have to add the corresponding forces, so that these hourglass modes are registered, they are not activated. So we need to calculate the forces. So for each of the generalized displacements qi, small qi, we define generalized forces
Sir,
capital qi. Yeah, yes
so
please.
is the physical representation of this generalized displacement?
Yeah, this is in you see, this is in a way is representing the hourglass deformations. This is representing the hourglass deformation. So for each of these we are having a scalar quantity. So gamma bar transpose into, if we take W, that gives you q1, the generalized displacement corresponding to W hourglass. If we take gamma transpose into theta x, it gives you the generalized displacement corresponding to theta x hourglass. Similarly, if we take gamma transpose into theta y, it gives you the generalized displacement corresponding to theta y hourglass. And we have to control these. So corresponding to these generalized displacement, we should have we need to apply forces. So these forces we define as, say, q1 is equal to some constant, although q1, q2, q3 in general could be coupled. So q1 might involve small q1, small q2, small q3, but I am taking here the capital q1 is only related to small q1, and so similarly others. So q1 is some constant c11 into small q1, and the generalized force corresponding to theta x hourglass is c22 into q2, and q3 is equal to c33 into q3. So we need to apply these forces. Of course, see here now the C11, C22, C33, these are the user input values. So if these values are too large, the element again would show locking. If these are too small, the element will not register hourglass, so it would show hourglass deformation. So you'll have to take the value such a way that no, the element doesn't lock, and at the same time it registers the hourglass deformations. So now we want to construct the stabilization stiffness matrix. So now the stabilization stiffness matrix is given by, so of course now you can look at the now the forces corresponding to these. But yeah, so now finally once we have defined these forces in terms of q1, small q1, q2 and q3, then we can talk of the generalized stiffness. So the finally the stabilization means to resist the hourglass modes. So the stabilization stiffness matrix, let me call that as kh, that is stabilization matrix to control hourglass, will be given by, so this is given by kh. That means, see, whatever we have kb plus ks, in that you are going to add this kh. So this kh is going to be, of course, yeah, here now the elements are written such a way that first w, all the w degrees of freedom are there, then all theta x degrees of freedom, then all theta y degrees of freedom, but you have to rearrange that. So that would be, say, c, let me write c11 as c1, because that's a single constant. So let me write that as simply as c1. So c1 into gamma bar no, gamma bar into gamma bar transpose, so that it is a matrix. If into gamma bar and then the null matrix, then corresponding to theta x, this would be null matrix, then constant c2 into gamma bar into gamma bar transpose and a null matrix, then a null matrix and a null matrix, and c3 gamma bar into gamma bar transpose. So this would be the stabilization matrix. So the stabilized stiffness matrix will be, let us say, ke, then that ke is going to be kb for the element plus ks for the element and plus kh. So if you add this kh, no, the element will not depict hourglass deformations, so hourglass would be controlled. Now one of the thing here is to how do we choose the constants c1 and c2. So actually I have taken this treatment from a paper by Belisco and Say. So this is International Journal for Numerical Methods Engineering, volume 19 and 1983. So this is taken from that paper, and that paper says that the constant c1 should be taken as c1 is equal to some constant no, the parameter rw into shear correction factor into shear modulus into thickness cube divided by 12a square, and then we have here b1 transpose into b1, so it would be scalar, plus v2 transpose into v2, so this will also be scalar. So this now all things are known parameters, you know, the shear correction factor, you know, the shear modulus of the material, you know, the thickness, you know, the area of the element, the matrix b1 and b2 are also defined. So only parameter is rw. So here rw is approximately taken as 10 to power minus 2. So if you do that, it doesn't depict locking, and at the same time it registers the hourglass deformation. So that is the value of c1 and c2. Similarly, if you look at c2 and c3, they are same. So let us say that these are to control the theta x and theta y. So r theta into d is the flexural stiffness, cs cube upon 12 1 minus nu square, that you know, 16a. And then of course here you have B1 transpose into B1 plus, see, these would be scalar. B1 transpose into B1 would be scalar, but when you are talking of these here, there is a transpose, so gamma bar into gamma bar transpose, this would be a 4 by 4 matrix. So there is a transpose over here, there is a transpose here, there is a transpose here. So, and this is, yeah, B2 transpose into B2. So this would be C2. R theta would be also similar to RW value. So this is what is done. This now this is to actually this is added in the stiffness matrix. And when you are talking of the large high strain rate deformation problems, so then similar kind of a matrix you can add in the as a damping. Similar kind of a matrix, the constants could be different, but you can add a as a damping. So that would be, this is stiffness stabilization. Similarly you can have damping stabilization. So this is what this hourglass control, that is how you can achieve. And in the another paper by Belisco, they have proposed another approach. So this is more BC, more rigorous derivation for the KH. But then there is another approach.
Here, what is R theta?
R theta is another constant. So say R theta would approximately be taken as 10 to power minus 2. This is a user input parameter. RW is a user input parameter. R theta is a user input parameter. And if you take these values too large, it would depict locking. If you take too small, it would not resist the hourglass deformations. So you'll have to choose a value something like this. From the numerical experiments, it is found that RW is approximately 10 to power minus 2 and R theta is approximately 10 to power minus 2. So another approach for this hourglass stiffness KH is directly what is proposed in this paper by again another paper by Belisco, that KH, and of course this KH is used for the basically selective integration scheme. So a constant epsilon, and then as stiffness you take the difference shear stiffness evaluated using 2 by 2 integration minus shear stiffness evaluated using 1 point Gauss quadrature integration. Take the difference of these two multiplied by a epsilon, and you add this as the stabilization matrix. Of course this will only control the W hourglass, because this is corresponding to that. And here you will see that epsilon would be RW into H square by A, and where RW is same, approximately 10 to power minus 2. So this is another way of, that's a much simpler approach, as you see here. Yeah, that you can also use this kind of stabilization matrix for this. So I think yeah, this is where I want to stop. If you have any questions and doubts, I can take few questions. I have another meeting at 12:15, so I have to wind up it a bit early. So if you have, please ask questions if you have. Yeah, any questions?
Sir, sir, who is the
Yeah.
TA of this course?
TA of the courses are actually one Mr. Sumit Kumar from the PhD, and Mr. Miss Neha Pandey. So if you have any programming related doubts, you can actually contact Mr. Sumit.
Sir, actually, I had a problem regarding the submission of the grades on the grade scope. So I have mailed you yesterday evening, sir, but I was not able to submit on grade scope. So I wanted to get in touch with TA regarding that.
Yeah, I will look at it. You have emailed it to me now, so I will look at it. Look at it.
Okay, sir. Okay. Thank you,
Yeah.
sir.
So this KH in the second approach will
Yeah.
add only to the shear stiffness, right?
Yeah, this will be added to the, now you will have, as I already said, no, element stiffness matrix is, you will have now for this case when you look at KE, so KE would be equal to KB, which would be for the element integrated over using 2 by 2 integration, plus you will have KS for the element which is obtained by one point integration, and plus you will have this kh. So this kh is given by this. That's what I have written here. And in the earlier case, what we have defined that kh matrix, in that kb is also evaluated using one point integration. So that was reduced integration. This is selective integration. Okay.
So when we are doing reduced integration, so we are
Yeah.
only finding the integral at one point. So
Yeah.
my question is, when we are finding integral at one point instead of 2 points, so
Yeah.
that integral can be more than or less than the exact value of the
No,
integral.
actually, it turns out that it comes out less actually.
But sir, I've seen an example in which if we try to find out Gauss quadrature using less number of integral points, so it can be more than also.
In this case, it actually comes out. So if you look at the diagonal elements, they would be they come out as less, not more. That is why we have to add an additional stiffness. And this additional stiffness is only affecting the hourglass modes. It doesn't affect the rigid body modes.
So why it is coming less? Is there any specific reason, or we have to
Uh,
do it? Then we will observe.
yeah, you have to check, numerically evaluate and check. Yeah, I don't have a region as of now. Yeah.
Okay, sir.
Yeah.
Earlier approach, you said that it was reduced integration for all the
Yeah.
methods,
Yeah.
means KB,
So here
KS.
when I have written this, KB is evaluated using one point integration. This is evaluated using one point integration, and then you are adding this KH.
Okay.
Any other question, doubt, anybody?
I am facing problem in MATLAB programming, sir. As I am learning now MATLAB programming, so I am a beginner like. So I am
But
facing
I think
problem
I
how
had
to.
covered, as far as the assignment is concerned, I had informed you well in advance when I discussed the classical Kirchhoff plate bend incompatible plate bending element. That time itself, I had told that this assignment is going to be there. So you should have started working from that day onwards. Yeah, but if you have some difficulty, 1 or 2 days is okay. I can give that much time.
Okay, sir. Thank you, thank you. Sir.
Okay, so if there are no questions, I'm stopping here. Thank you all for your
Hello,
attention. Yeah,
hello, sir. Sir, I have one
yeah,
question regarding this particular subject only, sir. So the question is,
yeah.
sir, what are the future research aspects like in FEM? Like currently, you are teaching us like we have read linear
I
part
am
also.
teaching what is already there. See, I am teaching
Yes,
what
sir.
is already there. But
Yes.
as far as the future research is concerned, either the applications of these two, say nonlinear problems, nonlinear elasticity problems, or nonlinear viscoelasticity problems, or viscoplasticity problems. So the applications of these two new problems is what I can say one of the future scope. And the other advancements are taking place, so rather than people are now working on mess free methods. So
Okay.
here we have a mess. Now without mess, whether can you solve a problem? So people are, and in that also a lot of research has undergone. But yeah, still people do come up with new techniques to solve different types of problems.
Okay, sir.
So what we are discussing here is the application of these two nonlinear elasticity problems and nonlinear viscoelasticity problems, viscoplasticity problems. So applications of these to those problems could be future research direction.
Okay, sir.
Yeah.
Thank you, sir.
Yeah. Okay. So, is there any other question, anybody? So, if there are no questions, I am stopping here. Thank you all for your attention.